In this video I will use simple examples for giving you an idea how a pattern for dealing with functions in assembly can look like. So a pattern for implementing functions and for calling functions. The examples will be very simple, simpler than what you see here. This actually will be the example where I show you in the end how it could be rewritten with this pattern in assembly. You see, this program does not have any global variables and the functions do not have any local variables. Also, the functions are very simple. They don't expect any parameter and they don't have a return type. Which is actually not entirely true. Recall that function main always has a return type implicitly defined in this case by the compiler, which is an integer, and it would return by default 0. Which then would be the exit code of the program. Here we mainly can ignore that fact. Also recall that on our architecture we have one instruction for printing a character. So for example, this putchar call will actually not be a function call. It simply will become an instruction for printing this uppercase B in this case. So actually function calls will only be here, here, and here. But before I begin, let's go through this example already. You see, when you compile and run it, it simply prints a few characters. But let's go through the control flow of this program, and then you already get an idea why something like a stack is required for realizing this control flow. So this is the prompt from the shell where we run the program, and then the execution begins with entering function main. Then the first instruction gets executed, which prints this lowercase a, which we then see on the terminal. Then we call function foo, which means we jump to function foo. We enter function foo and execute the first instruction there, which prints this uppercase F. Then we have another function call for function bar, which means we now enter function bar. We execute the instruction for printing an uppercase B, and then we return. Returning means we continue with the first instruction after this function call, which prints this lowercase f. Then we are done with function foo and we return to function main, which means now we continue there with printing this lowercase b. And then we again call function foo. And now, of course, things basically get repeated. And you also see that most of these jump paths will be the same. We again go to function foo, we enter function foo, we print again this uppercase f, again we call function bar, and when we enter function bar, we again print this uppercase b, then we again return, we return to the same instruction as before, which prints this lowercase f, but now there is a difference. When function foo now returns, it's returning to a different location, to the instruction which prints this lowercase c, of course. But this actually will be the big deal. And you also see here that this jump path back from function foo to function main is a path which is different from before. We have a different destination. Okay, but let's continue here with this example. After printing this lowercase c, the program prints this new line, which is simply a line break, and then it terminates. And that means now on a new line, the shell is ready for the next command, where you, for example, could check the exit code with echo $? But now actually let's do some assembly programming, and for that I want to use a simpler example with just two functions. And actually I first want to rewrite this program so that this implementation of function foo comes after the implementation of function main. So I want to move this down to here. And this, of course, can be achieved by using a forward declaration. And now the first naive approach would be to write a program which is exactly doing what we see in this ABC program. It's first printing this lowercase a. So the first instruction simply would be this put c instruction. And after that, some instruction later will be used for doing this function call. Let's leave it out for a moment. After that, we print the lowercase b, we print the new line, and then we terminate the program with exit code 0. So after this few instructions for function main, we now can write some code for function foo. Function foo should print this uppercase F. So the first instruction for this function would be this putc instruction here. And now we can think about how to actually do this function call. The simplest way would be to give this putc instruction a label, foo, and then we can use a simple jump instruction. We simply jump to this labeled instruction, and that means returning from this function also could be done by a jump instruction. We could use a label, ret for return, for the instruction that follows this function call, and that means returning from function foo would simply be a jump to label ret. Now it makes sense to run the program in the debugger to see the control flow of the program, and for that it also makes sense to have a close look at the instruction pointer, also at the memory locations of these instructions. The first instruction is located at address 0, then second at address 4, and so on. And we have in total 7 instructions, so the size of the program is 28 bytes. Then the execution begins with the instruction at address 0. This prints the lowercase a. Then we have the second instruction at address 4, which will actually be this call instruction for function foo. That means the return address is 8. Then we jump to the first instruction of function foo. Now the instruction pointer becomes 20. Then we print this uppercase F, and then we jump back to the return address, to address 8. There we print the lowercase b, then the new line, and then we terminate the program with exit code 0. But obviously using simple jump instructions for realizing function calls and using labels to denote the return address doesn't work in general. Like in this example, where we have 2 calls to function foo. And the return address for the first function call should be the address for this instruction printing the lowercase b, and the return address for the second call should be the address of the instruction printing the lowercase c. Using the same label to mark the 2 different return addresses doesn't work because a label is identical to an address. It's just a symbolic representation. So you cannot use the same label twice. If you would use different labels, then you have the problem that returning from the function cannot be realized with a jump instruction because you either have to specify the first or second label. Now to motivate the solution to this problem, let's consider again the addresses of these instructions and the value of the instruction pointer when each of these instructions gets executed. When the first instruction gets executed, the value of the instruction pointer is 0. When the second instruction gets executed, the value is 4, and the return address should be 8. So instruction pointer plus 4. When we print the lowercase b, the value of the instruction pointer is 8, and when we call foo a second time, the instruction pointer has the value 12. So this time the return address should be 16, 12 plus 4, which is hex 10. And this actually will be the idea for the instructions that we can use on our architecture for function calls. It provides instructions that do a jump to a certain destination address and leave behind in some register the return address. And this return address always gets computed by using the current value of the instruction pointer plus 4. And this way, the called function, the callee, does know to where it should return. Actually, there are 2 instructions for function calls provided by the architecture. The first instruction expects as first operand an immediate value. So here you can specify a label, which will be used as an offset for a jump. So you can specify here where you want to jump to. And the second operand will be used for leaving behind the return address. So in the second operand, the current value of the instruction pointer plus 4 gets stored when this instruction gets executed. The second variant expects 2 registers. The first register for specifying the destination address and the second for specifying a register for the return address. The reason to have here actually 2 instructions is simple. if you have a very large program, then in general you cannot use immediate values to jump to an arbitrary address. In general, the addresses are 64-bit addresses, and the second variant allows you to first load the 64-bit address somehow into a register and then use this instruction to call a function which is somewhere in memory. This second instruction can be written in different notations. They are all equivalent to each other. For example, you can write jump instead of call, which basically has the same meaning. And there is also one variant which makes clear that there is another purpose for this second instruction. If you simply write ret and specify just one register, implicitly it means that the return address is stored in register 0, which means that you are not interested in the return address. And of course, this instruction can be used for returning from a function, where you just want to specify the destination and you're not interested in leaving behind a return address. What I will use in the remaining examples is for calling a function, this first variant, because the programs are not very large, so this always works. And for returning, of course, I use this ret notation for this second instruction. With these two instructions, the program now easily can be implemented. We have here the two function calls, and here we return from function foo. Now let's again use the debugger to check the control flow, see how the instruction pointer is used to actually compute the return address and how the return address gets stored in register 1. Now with the first instruction, we again print this lowercase a. Then we have reached the instruction for the first function call at address 4. That means the return address will be 8. And when we execute this second instruction, you see that in register 1, we now have the value 8. And now we execute in function foo the first instruction at address 28, which prints this uppercase F. Then we reach the return instruction, which will jump back to address 8. And there we print the lowercase b, and then we have reached the second call of function foo. The call instruction is at address 12. That means the return address is 16, or hex 10. When we carry out the second call, you see in register 1 we now have hex 10. Then we again print in function foo the uppercase F, and then again we return to the address stored in register 1, so to address 16, which means that we next print this lowercase c, then the new line, and then we terminate the program with execute 0. Now this pattern works very well when you have functions that do not call other functions, so-called leaf functions. But let's go back to the original problem where we have actually two functions, foo and bar. And here bar is a function which is not calling other functions, so a leaf function, but foo is calling bar. So this is a non-leaf function. But let's use the debugger to see what would happen if we would use this pattern also for this non-leaf function foo. So after executing the first instruction, we have this lowercase a and have reached the call instruction for function foo. The return address is 8, and after executing this call instruction in register 1, this address is correctly stored in register 1. Then we print out the uppercase F, and then we have reached the instruction for calling function bar. The return address here is hex 2436. So after carrying out this second call instruction, register 1 now has the value hex 24. And that means after printing the uppercase b, we correctly return to function foo, to the instruction printing this lowercase f. And then we have reached the return instruction in function foo. But now register 1 contains the address hex 24. That means now we jump back actually to the instruction printing the lowercase f. And this is actually an infinite loop. So actually you see lots of lowercase f's. Now the solution for supporting non-leaf functions will be to use the stack to push the return address when we enter a function on the stack, and when we leave the function, we pop the return address from the stack. Now for implementing the stack, the implementation should be efficient and simple. Consider that the first part of the memory is used for the instructions of a program. In our case, we just have a text segment. In general, of course, we also have global variables stored in the data segment if they are initialized, and the PSS segment is used for the uninitialized global variables. So what part of the memory could be used for the stack? We basically use the second part. And it actually will make sense to start at the very end of the memory and let the stack grow from right to left when we push something on the stack. For the implementation of the stack, I will use one register, register 1, for pointing to the top of the stack. And to make the program a bit more readable, I use this EQ directive so that the assembler is replacing SP with 1. Initially, the stack pointer will point to the end of the memory, and for that the stack pointer gets initialized with 0 when the program starts the execution. Now it might be strange that I'm initializing it with 0 so that it's actually pointing to the end of the memory, but let's assume that we have 64-bit addresses, which is actually the case for our architecture. Then if you have initially the value 0 and you would subtract 1, it would point to the memory location with address 2 exponent 64, 1 less. You would have this overflow when you subtract 1 from 0. And this is the address of the last memory cell. And the nice thing is that this also works for architectures where you, for example, have just 1 kilobyte. Then you have 10 bits for an address. And if you consider the last memory cell, the address of that would be 1023 or 2 exponent 10, 1 less. So this is independent actually on the size of the memory. So this would be the initialization of the stack, that we initialize this register with 0. When we push an address on the stack, the size of an address is 8, then this will be realized with 2 instructions. First, 8 is subtracted from the stack pointer, so we basically move it to the left by 8, and to this address we write the content that we want to store on the stack. So this will be a store operation. Now in the next examples, register 2 will always contain the return address when a function gets entered. So this would be the push operation for register 2 to push the return address on the stack. When the function leaves, it has to pop the return address back into register 2, for example. And this also happens with 2 instructions, basically the way around. First, from this address stored in register SP, 8 bytes are fetched into register 2, and then the stack pointer gets incremented by 8. So basically that's already the pattern. When we enter the function, we push the return address on the stack, then we have all the instructions of the function, and at the end, when we leave the function, we first pop the return address from the stack, and then we have the return instruction. Now here this pattern was applied to the initial example, at least for function foo and function bar. You see, this is the code for function foo. It begins with these 2 instructions for pushing the return address on the stack. We will call this the prologue. And it ends with these 3 instructions for leaving the function. 2 instructions for popping the return address from the stack and then returning to this return address, the so-called epilogue. The same pattern is here also applied to function bar, even though here it's actually not necessary to use this pattern because it's a leave function. So one optimization would be to not push the return address on the stack and also not to pop it, of course, then in the end from the stack. But with optimizations we can deal later. First of all, it's interesting to have a pattern which always works. Now before I show you the execution of this program in the debugger, let's first go over a few of the function calls first manually by going through the program step by step, and maybe also a few returns from function calls. With the first instruction, you just initialize the stack pointer. That means you do not see any change in memory. You just set register 1 to 0. Then when the call instruction for function foo is reached, look out for the return address. It will be hex C. And then with the first two instructions in function foo, this return address actually gets pushed on the stack. First, the stack pointer gets moved to the left, which means you see a change in register 1. And with the second instruction, you see a change in memory. So the return address stored in register 2 will be copied into memory to this top of the stack. Then when the second call instruction is reached for function bar, the return address is hex 30. And again, with the first two instructions in function bar, this return address is pushed on the stack. So again, first the stack pointer gets decremented by 8. So you see a change in register 1, and then you see a change in memory. So you will see in memory the return address hex 30. Now when we leave function bar, the return address is restored. We do this pop operation. There you first do not see an effect, because when this return address is fetched into register 2, basically the same value gets copied into register 2 that was in register 2 already, because bar is a leave function. So here this pop operation actually wouldn't be necessary, but you will see that the stack pointer gets incremented by 8. It gets moved to the right. You will not see that the memory location gets changed. Simply the memory location left of the stack pointer is now invalid. Then after returning to function foo, this character gets printed, of course, and then the return address for function foo gets restored. So here you actually do see an effect when the first instruction fetches the return address hex C into register 2, and then again the stack pointer gets incremented by 8. So now the stack is again empty when we return to function main. And here the next call instruction will have the return address hex 14. And then you will see that things basically get repeated, but with different addresses on the stack. So the first return address will be this hex 14. The next again will be hex 30. Now with that pattern, we also can turn function main into a regular function. That means it also begins with this prolog. It stores the return address on the stack, and it also leaves with the epilogue. So it pops the return address from the stack and returns to it. This will mean that function main actually no longer has to be at the beginning of the program. At the beginning, we do in some startup part all the platform-dependent things, in our case initializing the stack. In general, things like initializing the BSS segment might happen here, which is the case on Arduino, or other platform-dependent things. Then comes a call to function main, and when the function main returns, the program terminates with execute 0. Later, when we deal with return values, actually the return value of function main will be the exit code. So that means we also have a pattern for writing a program in general. In the beginning, we have this platform-dependent part where in our case we initialize the stack and where we call function main. And after function main returns halt the program. After that, we have a list of functions which can come in an arbitrary order, like for example here in the order we specified them in the ABC program. And then of course you can choose whether you do optimizations for leaf functions or not.